because quantum is cool, and people need new things to do. If they can find a way to pretend, like quantum computing somehow applies to what they're researching, then by God they will. Yeah.
Up there, why is it? Oh, it's thinking about it. You know, I like sitting in the
It's hard to say in advance, but yes, that's what I did. So we're the same
You don't like grow face hair?
My expression was right.
You wanted it.
Well, I know.
Well, they probably that it is true.
And I was kind of reading it backwards. His starting index was 0, my starting index was 1. I could not understand that it could add be at 0 even when you subtract together, you added that one integer by bringing it back.
No, what I specifically mean there referring to is if I do this.
No, I did not realize I had to change my value.
Start out.
Instead of
I know.
instead of those being a program,
When I showed them class, I'm like, hey,
it's actually going down to G.
it's not obvious.
Like basically taking quantum computing.
So, thank you for coming in. I guess my name's John, I'm a math teacher here. And thanks for coming in on a Friday afternoon to see this. This is our first Dead Mathematicians Society Talk of the Year. And we started off with Roger Ford, who I just have to say is one of my mentors. When I started teaching, I was at Sandy High School, just a young puppy. I'm going to teach, and I still love math. And he was the same, but he wasn't a young puppy. But we would always nerd out together. And one thing he was always interested in, it seems, was counting things. Like, look how many ways we can fold this map. I'd be like, Roger, that's weird. I wouldn't say this. I would think, oh, that's kind of weird. But then these amazing patterns would come out. I have a feeling he's been working on this problem a while.
Yes,
So,
and no.
right. So we'll get him started. I'm sure there's time for questions.
Yeah.
Thanks for coming.
Yeah, John and I did start together, and I was his department chairman for a while. And one of the things I would go by his room, and there'd be a lot of laughter. Now, how many math classes do you have where everybody's chuckling all the time? And it would always raise, what's going on in there type of thing. Except later on in the hallway, I bumped into some of the students, and they were talking about how excited they were about mathematics. So he got them pretty fired up. He did a good job. So, we were nerds back then. Kind of pushed each other along. We're still nerds. Okay, sorry. But one of the things I always used to enjoy was, as he said, counting problems that came from the field of combinatorics. Now, combinatorics, how many people got a class in combinatorics? A few, okay. All right. It's not offered very much. I got my degree at the University of Washington, and combinatorics, I thought I'd go back and review. It's offered one class a year. So not many people have an opportunity to take that class. But this, I think, is a good definition of combinatorics. And mostly what you're doing is you're counting finite and discrete options. Fair enough. Let me give you some problems that kind of got me interested in this area. There's a puzzle book. They were talking about stamps. The stamps still come in sheets, and you can pull off a certain amount of stamps at times. And if the stamps are attached by a side, or a top and bottom. Now, if we have two stamps, how many different patterns can we have? Well, there's only two ways of doing it. And we're saying you can't turn it upside down. We're not counting that as a different, keeping them in the right orientation. So there's two possibilities. Suppose we move that up to 7 stamps. So we're looking at something like this. This is a good problem in combinatorics. There's no known formula, or at least there wasn't when I was researching this. It seems like a simple problem. It's a problem which you can explain to somebody at a pretty young age. Oh yeah, how many different ways can you pull out the stamps? But we don't have a formula for it. It seems like we ought to be able to do it. This is something readily available, easily done on a computer, and this is one of the reasons combinatorics has become more and more popular. But the answer is 760 ways. So now you can give somebody that question and show how smart you are. Okay, 3x3 stamp, map. And John was talking about, take a map, 9 rectangles, and we can fold it up. And we can fold it up in a different way. And then we count the different ways by shooting an arrow through it. So the first page is number 1 in this case, and then it goes 3, 2, 5, 4, oops, I forgot 6, 4, 7, 9, 8. Okay, that's one pattern. How many patterns can we come up with? 1,368. Okay, but it's a problem you can easily describe. It seems like something simple that we ought to be able to do, but we don't have a formula for it. Again, it's on program. Now, this one is one that is my favorite. I've been working with this for a lot of years, called the semi-meander problem. Now, what we have is arches on the bottom, 4 arches. These are supposed to be arches, but they're hard to draw. Okay, on top we also have 4 arches. But here's the conditions that have to be met. We have to put 4 arches on the top in such a way that if you trace over the whole pattern, it passes through all the arches, and returns to the starting point. Now, this one I know is unsolved. With 10 arches down here, there's 1,406 ways of doing it. Okay, and again, all computerized, all done by hand. You can't do it by, well, you can do it by hand, and some people have tried doing it by hand, but we have taken it on a computer to over 25 million. So, again, no formula though. It seems like there ought to be a simple formula for this stuff, but there isn't one out there. And this area, this combinatorics area, is becoming a lot more popular because we're getting more and more computers out there. Now, the one that we're going to be talking about here is, it's called die cast. Now, it looks like it's Dick, and I will probably say that because I said that for years and just learned the correct pronunciation in the last few months. So, what we have is a grid on its side, and what we're trying to do is we're trying to find all the paths that start here and finish there. Now, there's not lines here. This is just counting how big our grid is. And our grid here is 7. That's called a semi-length. So the semi-length of a die path is the spacing down below. Now, the paths we can go, starting here, we can go up, down, but we're always moving to the right. And the question is, How many paths can we go? Well, this one we know the answer to. And it's called the Cadlin number. And if you've been involved at all in combinatorics, the Cadlin numbers is one of those sequences that comes up more often than almost any other sequence. I'll show you how we can do it. Okay, this is what the grid looks like that we're traversing. Notice there's no lines here, but this is for what we call a semi-length of 4, because there's 4 spaces down here. We're going to start here. We're going to go up 1. Thank you. And there's 1 path to get to there. Everybody's going to do that as the first step. Now, from here, we can go down here, or we can go up there. So there's 1 path here, and there's 1 path here. Now, the next one is 1 path here, but to get to here, we've got 2 paths. We can go to here, and come down, and we can go here, and come down. Or go up, excuse me. So there's 2 there. And if we keep doing this pattern, 1 and 2 makes 3. Down here we have 2. Up there we have 1. So here and here, there's 4 different paths to get there. We've got 3 to get to here, and then 1 going up from down here gives us a total of 4. Here and here we've got 5 paths. Here and here we have 9 paths. We've got 5 here. It's 5 and 9. So from here there's only 1 path back down. So there's a total of 14 different paths we can get to the end. Now that's with 4 spacing here. If we had 5, then equal 5, we'd have 42. And this is the formula for it. It's called the Cadlin numbers. And if you looked it up, you'll find dozens and dozens of examples of how this shows up in the real world. Oops. Now, all these formulas, there's going to be a lot I'm going to be showing you. I'll put them all up on one page in a little bit. Okay, now, going back to this, since we know the number, we're looking at traits with dict paths. And one of the traits is called peaks. Okay, that path has 7 in length, it has 3 peaks, and it has 2 returns to the x-axis. Okay, and that's what this is here. This is peaks, and this is returns. So those are traits of the dict path. And I've come up with a conjecture dealing with peaks and the returns. But what I'm going to have you do now is on the reverse side of that sheet, right there that I gave you, see if you can find the 14 paths. So see if you can draw on all 14 paths right now. And everybody came prepared for class, right? Brought pencils and erasers.
Help yourself to some coffee.
Yeah.
Does it want to look there? Yeah, look at that can. Mention the next one through.
That's the semi.
Yeah, let's do it.
To get from point A to this is A and this is B.
No, more systematic. Are you just the lowest part?
This is fast.
Yeah.
Distracted because I can't see. That's true. Yeah. You over here? I'm just trying to find how many paths we can get through.
All four syllables. I hate drawing pads.
Now, one of the things this forces you to do is try to be systematic. And if you're a programmer, how many people program you, out of curiosity? Okay, if you're a programmer, you know you have to think in terms of breaking something down in a way that you make sure you cover all the possibilities. And a good mathematician always has at least 3 mechanical pencils with them, good erasers so they can handle this.
What did you just insinuate about me? We're great. So, whatever you are, you're not merely good.
He started trying on one. And I was like, wait, I can't count.
Fill in the grid too.
I gave my pencil away. I gave my pen away. So now I'm just imagining. Thanks.
It's either that or we can transfer that and give it.
That's all right.
Classes, if I have students doing something like this, I tell them this is a pop quiz and they have to get 100% to get credit. Of course, the rule is, on my pop quizzes, you can cheat. You can ask your neighbor, you can look at your neighbors, and if they don't help you, you can give them a dirty look. Or you can raise your hand and I can come around and help you. Take the pressure off. Okay, if you've thought about it and had a chance to think about it, one of the ways you might have thought about doing it is maybe finding all the ones that reach the highest level, and then all the ones that come up to the next level, and all the ones that only go up to the second level, then all the ones that only go one high. And so there are different ways of breaking it down to try to find all of them. Okay, I'm going to put them up here now, just so you can see. Just in case. Not quite good fit. See. Okay, it does fit. I sometimes marvel when I look back at some of the formulas people had come up with in combinatorics, and they had to do all this stuff by hand. amazing how accurate they were. Okay, I'm going to put this up here. Now, this is the same one you just did, except what I was putting up here, P is for peaks, and R is returned to the x-axis. So when we started, we don't count that as a return, but like this first example right here. Okay, we have one peak and one return. Okay, this example here, we've got two peaks with one return to the axis. This one's got two peaks and two returns. Okay, I don't expect you to figure that out on all of them. Okay, don't write them in. But this is going to be part of the conjecture that I'm getting to. The peaks and returns. But here's what I want you to do. Down in that table in the lower right-hand corner, I want you to write these numbers in. Now, how we read this table is this. Looking at this number right there. So, what we have is a dyke path, link 4, two peaks, two returns. The answer is 3. So there are exactly 3 paths with that trip. And if you add them all up, okay, we got 7 and 7, we got 14, so we all pass covered there. But hold on to that. Write that in on that table down there at the bottom. Now, I've been working on the semi-meander problem for years and years, and I got kind of stuck. And so I went to a website called Math Overflow. Have you ever heard of that one before?
No.
Nick's heard of all of them. Math Overflow. And I'm going to read this to you because it's so small. It's a question and answer site for professional mathematicians. It's built and run by you as a part of the Stack and Exchange network of Q&A sites. With your help, we're working together to build a library of detailed answers to every question about research level mathematics. We're a little bit different from other sites, and here's how. Ask questions, get answers, no distractions. I looked up combinatorics, and I was trying to find something on semi-meanders just to get a new approach. And I typed in returns and peaks, and up popped this question from somebody. And they had the name, and I never remember it. And here's what this person asked. He said, the number of Dick paths with K returns and B peaks. The number of Dick paths has so many touches. Now those are returns. You're talking about touches coming back. So there's a formula for the number of returns, and that's actually called the Cadlin triangle numbers. So it's well known. So like when you're looking at the one we just had, that would be these numbers coming down. So if we're looking at the number of returns, this would be, let's see if I get something here in right dark. 5, 5, 3, and 1. We have a formula for that. Then this person went on to point out that there is a formula for the peaks. Okay? The peaks are the ones going across. 1, 3 and 3 is 6, 1, 2, 3 is 6, and 1 going across is 6. And this is called the Narayana numbers. And I think it's actually Narayana triangle numbers, and we go through more than Narayana triangle numbers. Now, in both of these cases, the Narayana numbers and the Catalan numbers, triangle numbers, sum up to the Catalan numbers. So both of these formulas are just subdividing the Catalan numbers. We had 5531 is 14, 1661 is 14. So we've just subdivided the 14 in two different ways. So this is the question. What is the number of dict paths which have both K returns and BPs? So we know the formula is going across and the formula is going down, but we don't have a formula for a single cell. So like the one on the front of the page, I gave you what we started with. We don't have a formula for that. That one single cell. So he's asked me what there was, and he said he couldn't find one. He did research. So I decided I'd do some research too before I tried tackling the problem. And this is where, okay, you need some help, Nick. Touch panel in the door. That was tough.
Whoops, there.
Okay. Online encyclopedia of energy sequences. Now, Nick's heard of it. Anybody else heard of it?
Yeah.
Okay.
It's amazing.
Yeah, that's right.
Checking the sequence and it spits out the.
Back in 1964, a grad student at Cornell named N.J.A. Sloan started collecting integer sequences. And he actually produced a book called The Handbook of Integer Sequences. Not a bestseller at the time, but he kept doing this. He kept collecting them. And eventually in 1990s, they decided to put it online. And now it's got over 250,000 entries into this website. When you look it up, all you have to do is type OEIS. This will pop up, and we get to that page. Now, if you're looking up some information, this is a great site. So one of the things I did is I typed in dike paths to see if I could find anything on it. And I typed up dike paths, and I typed up peaks, and I typed up returns, and there was nothing there. But the number of entries surprised me. With dike paths, there are now over 900 different entries about dike paths. So a field there, how many have heard of dike paths again? Nick? Oh, okay. So a real small area in the area of combinatorics has over 900 inches on this website. So if you want to find out something, this is the place to go. And I didn't find anything on the peaks and returns. There was no, nobody had come up with anything yet. So I believe this person when they said they hadn't found anything. Now, this website, fantastic. Now, I'm going to type in sequence here. And I think a lot of you will recognize this. So, okay, yellow if you got it. Yeah. Fibonacci. And if we hit enter, okay, Fibonacci sequence here. And if you type in a sequence of numbers, okay, you notice it popped up right here. You don't have to have the first ones. It'll find it if it's in the sequence. And that's what's wonderful about this. So if you come up with a sequence, even if you don't have the beginning one, if you have a certain number of digits, it'll find it for
Would
you.
they have to be consecutive, or you could just grab?
They need to be consecutive.
Okay.
One of the things you got to do though, is depending on what numbers you type in, you need to type in a lot of numbers. If you just type in a few, you may get back, 70 sequences that have that sequence in it. So you have to be fairly specific with it. Yeah, that's one way of accessing the sequence. Another way is to type in the name. So if I just went back up here and I typed in Fibonacci, well, maybe let me try something else. Let's just type in. And we got to spell it right. We're pretty particular about that. And we hit search. Okay. And okay. Now I don't know if you can see this right here. It says there are now 904 entries under DICPACS. That's a lot of information. So let me show you what's going on down here. If we go down here, comments people have made, different entries by different mathematicians, Maple program, Mathematica, and Prague, and I forget, isn't that another program? Cross references, these A numbers. We go back here to the top. The third way of accessing this information is through an A number. See right here we have A057163. That's another way, if you know the number of the sequence, you can just type that in and it'll go right to that sequence. And all these other ones that are highlighted in blue, these A numbers, these are other sequences that mention DICPAC. So this is a tremendous reference. On and on and on, and showing the work of other people, and then they formulas. Okay, oftentimes they'll show you many different formulas for getting that particular sequence. You may know one way of getting it, with factorials, but maybe there's a different type of function. There's a summation. Any type of, there's a lot of different ways, and one may be useful to you. But this is a great resource for that.
Do you have a contribution on there, Roger?
Yeah, I've got several. But one of the things you need to realize is you make contributions on here. This is not the same standard as if you're writing in a mathematical journal. The mathematical journal, they're going to check everything you've done. Here, they check it for some things, but they're not saying that what you're saying your particular formula necessarily does that. What they will do is attest to the fact that your formulas are correct, and it does generate viable numbers. So they'll check at that point. But a lot of these references go back to textbooks and journals, math journals, that you can access and look up stuff. So here are 3 ways you can access it. Oops. Go back. The name, the A number. Every new sequence is given an A number, and then typing in the sequence. And sometimes it's kind of fun to put in not the whole sequence, but you'll find out if you're trying to guess a formula for something, if you put in part of it, it'll give you a whole bunch of different sequences and different formulas, and maybe one of them will work for what you need. Anyway, going back to that person, I tended to agree with him. I couldn't find anything. So I decided I'd give it a shot. One of the things that I do quite a bit is program on a calculator. So I'd already been doing peaks and returns with semi-meanders. So I just switched over and changed it peaks and returns for diagonals. In doing that, we got a number of arrays. Okay. This is the one we just did right here. This is the one with n equals 4. And you can see the numbers right here. Okay, this is the solution set for n equals 5. So, example, this right here, that would be for semi-length of 5 with 3 peaks, 2 returns, equals 8. And I kept doing this, I'm getting more and more data. And this is what it looks like for 6 and for 7. Okay, what you notice is we're getting bigger and bigger triangles because the semi-length is increasing, so the number of possibilities with returns and peaks keeps going up. So I'm going to show you some of the formulas dealing with this. Table of numbers, okay? This is the total solutions for semi-length of n. Catalan triangle numbers, okay? This is the formula when we add up the columns. Like in this column, like on this array for n equals 5, if I added these up, I get 14, 14, 9, 4, and 1. If you add those up, you get to 42. That's the formula for the returns. This is the narrated triangles. This is the one that's going to give you going across the peaks. Now, another one, a pattern in here. I think a lot of you are probably familiar with binomial expansion. How many have done binomial expansion? Okay, a few. Okay, these can be taught to everybody. Also called Pascal's triangle. Does that ring a bell? Okay, maybe that's a better way of doing it. If you look on the diagonal here, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Now, Pascal's triangle looks like this. So you start with a 1, put a 1 on both ends. Now we just add these two to get a 2. Put 2 1s on the end. Add this, add this. Okay, and you can see the pattern, just keeps going down, putting the 1s on the end and adding the 2 above. Okay. Pascal's triangle. Well, that fits. We have 1, 5, 10, 10, 5, 1. Okay, here, n equals 6, we have it again. Right there. Okay, so there's another pattern in there. Now, another one, these numbers here in the first column, going up and down, turns out these are the Narayana numbers. Except it's one generation previously. So this would be the Narayana numbers for n minus 1. But if we're looking at this list of formulas, what's the one thing you notice about all the formulas? They're all dealing with factorials, right? Okay, so that was kind of a tip-off of what direction I might have to go if I was going to try to solve this. We've got a lot of factorials here. We've got a lot of patterns of factorials within each of the solution sets. So this is going to be interesting. One of the things that's fun about mathematics is we can play with blocks. We call it work. Solution set for n equals 1 looks like that. Solution set for n equals 2 looks like that. Solution set for n equals 3 looks like that. And the one we did, that's the solution set for n equals 4. And I think, yeah, okay. Solution set for n equals 5. Now, if we're going to get the solution for this, all of these arrays, what's happening is we're going to put them together like this and build them right on top of each other. So the conjecture I'm trying to come up with is something that's going to try to find every cell in this shaped object, which actually turns out to be tetrahedron, like this. Now, I'm going to try to put it up here, but I don't think you're going to be able to see it very well. But if we take them off one at a time, you can see how they grow each time. And we get this, I call it a lovely tetrahedron. And we look at the sides. And the bottom in this case, that's not going to show it very well. This is the solution set for 9. Now, one of the patterns down here, we got 1 through 8 going across. Anytime you see 1 through 8 through there, that means it's for 9 because it goes one more position. So that would fit just like this. So we're getting this great big tetrahedron. In other words, it's a three-dimensional object with triangles on every side. And we're trying to come up with all the numbers on every level. One thing I forgot to tell you about Sloan on the OEIS. He has been called one of the most influential mathematicians in the last half century. Unlike, say, Benoit Mandelbrot, who discovered fractals, a whole new field of mathematics. Unlike Andrew Wiles, somebody who solved a math problem from Oswald's theorem that was unsolved for over 300 years. He solved it with the help of a grad student. Here's a guy who's considered one of the most influential people in mathematics, and yet hardly anybody's heard of him. And the reason is that website has been used by so many mathematicians. They keep saying, I couldn't have done it without the help of OEIS. And so he keeps getting praised that way, and his name keeps getting recognized. So, very influential. Okay, I was going to tackle the problem. And the first thing I looked at was scenario like this. Okay? That's the solution set. And we already said we know a whole lot about the triangle. This is an obvious pattern. This one going this way is Pascal's triangle. This is narrating the numbers once removed. The total is the Kaplan numbers. And we know going across, we have the Mariana numbers. And going down, we have the Kaplan triangle numbers. So it seems like we've got a lot of information already. So the idea is, let's take a look and see if just working on the inside would work. So one of my first thoughts was, okay, I'll just look at the inner triangle, because the other stuff seems pretty obvious. Didn't work. Didn't get anywhere. So I took a new approach. And actually, I wrote this up this morning. This is our solution array. That's what we're aiming for. And what I thought is, what I could do is multiply maybe 3 arrays together to come up with the solution array. Now, one of the things I knew about these arrays is I was going to have to use factorials in here, right? Because everything looks like it's got factorials. So this is my strategy. I took the solution array and I said I'm going to divide it by my first array that I'm going to come up with. And I'm going to get a new solution array. Now, how do you pick that first one? Well, what I wanted to do was come up with a new solution array that has smaller numbers in it. And I also wanted to come up with something that had all whole numbers. I didn't want anything with fractions. I figured that that would be off. So the first array I came up with was something I called the multiplier array. And what I'm going to do is just multiply the rows by this array. So, row 1, row 2, row 3, row 4, row 5, row 6, and row 7. But to see how that's going to fit in with my final solution, my first step is to divide by that array. But you can see, now how did I pick up these numbers? Because every time I went down a lower level in the tetrahedron, these numbers divided into the numbers that were already in the solution array, and I still got whole numbers. So I kept going more and more down. And you can see the pattern. This one would be n minus 1, dot, 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 all the way to n minus 7. And it would be divided by, in this case, the factorials keep going up 1, so it'd be divided by 7 factorial times b factorial. All right, so giving you an example of that, this is the solution array for n equals 5. So I divided by my multiplier array. And I came up with, so this is the new solution array. So I got these numbers. Okay. Interesting. Did it do much good? I don't know. The numbers are different. Gives you something different to look at. So then I came up with, I said I got to come up with another array. So this time I came up with what I call the numeric array. Now this one, I'm not just dividing into the rows, I'm dividing into each element. So this is going to go into the first element in the first row, first element, second row, first element, second element, second row, first element, second element, third row, first element, second element, third element, and I'm dividing. And the pattern could be continued. So down here would be n minus 2, n minus 3, n minus 4, n minus 5. This one would turn into n minus 3, n minus 4, n minus 5. This one would be n minus 4, n minus 5, and then this one turns into n minus 5, and we have the 1 on the end. All right, that's the progression, okay? What happens when I divide by that? When I divided by that one, okay, so I'm dividing this into this, and I come up with this new array. And I'm going to call this one the D array. Now, what was exciting about that is the following. The D array turns out, it turns in for every single triangle turns into the D array. If you took the tetrahedron and you shot an arrow right down in the top, it would turn into 1. If you took it in the next one and shot an arrow down, everything would be turned into 1s and 2s. And if you go into the next row, the third row over, okay, so we're looking here, this would turn into 1, 4, and 6, all the way down to the bottom.